Hi, I'm Alex Boerle, a PhD student in the Visual Computing group at Ulm University. On behalf of my awesome co-authors, I want to show you a novel way of visualizing CNN architecture figures for publications. At the end of this talk, all of you should be able to add such figures to your papers within less than 10 minutes. When looking at the main computer vision conferences, ICCV and CVPR, we saw that the number of neural network architecture figures in publications has constantly grown. However, these figures are still mostly handcrafted and do not convey a unified design language. The manual creation of these figures complicates knowledge transfer, takes valuable time that could be spent on experimenting or writing, and might even introduce errors. But why are such figures still manually created? Let's look at current tooling for generating neural network architecture figures. First, we see some of the most popular neural network architecture visualizations. Here, we see Netron, Cafe's Netscope, and TensorFlow's TensorBoard visualization. While these visualization tools allow for very detailed inspection, they are not designed for use in publications. Their vertical layout and display of each individual layer make them powerful for analyzing neural network architectures in detail. However, this also prevents them from giving a high-level overview and fitting on a page for publication. On the other hand, are tools that have been explicitly designed for the creation of publication figures. Here, we see ConvNet Drawer and Draw ConvNet. While these visualizations provide an overview of the network architecture and can fit into publications, they do not support many modern network architectures, as they lack aggregation tooling and do not support parallel execution steps. To automate and unify the creation of modern, convolutional neural network architecture figures, we propose Net2Vis. With Net2Vis, CNN architecture visualizations can be created directly from the program code that defines an architecture. We designed the visualization grammar used in Net2Vis based on existing visualizations and expert feedback. To analyze existing visualizations, we extracted all neural network architecture figures from ICCV and CVPR between 2013 and 2019. We then labeled these figures based on how they visualize different aspects of neural network architectures. Based on these insights, we propose a visual encoding that communicates both properties of individual layers as well as overall model properties. I am first going to talk about how individual layers are visualized in Net2Vis. To convey what type of neural network is at display, the layer types that we use to build up the architecture need to be communicated. Most of the visualizations we extracted from papers only use textual descriptions for the layer types. Some also use text and colorized layer glyphs. However, as layers are often reused within one architecture, textually describing each layer can be repetitive. Thus, we propose to color code the layer, employing a visually dominant channel for this important property. Colors are assigned to new layers based on color presets, either using visually distinct colors or drawing from a color palette. Users can always adjust the color of each layer type to match their desired appearance. To map these colors back to layer types, our visualizations include a legend. Seeing the change of the spatial resolution can help understand the data transformation within a neural network. To provide this information, we map the height of the layer to the spatial resolution of the data it is operating on. Even though glyph shape is the most common encoding of the spatial resolution, not all current visualization encode this property the same way. For some visualizations, the height of a downsampling layer already conveys the changed resolution, while others display this change in the following layer. To prevent this ambiguity, and as the spatial resolution changes based on the internal workings of the layer, we visualize this transformation by applying different heights to the input and output of a layer glyph. Closely related to the spatial resolution is the number of feature channels per layer. In combination with the spatial resolution, the number of feature channels indicate the important transformation into and out of latent space. We define a glyph shape based on both the spatial resolution and the number of feature channels. This is done by mapping the glyph width to the number of feature channels of a layer. Contrary to the spatial resolution, which is derived from multiple layer parameters, the number of feature channels is based on one user-defined value. Thus, we employ one fixed width value for each layer. Next, let us zoom out and look at how layers can be combined. The most important factor here is the order in which the layers of a neural network are executed. Most visualization tools use vertical layouts. As these tools are designed for debugging neural network architectures on a computer screen, where scrolling is a common interaction pattern, this works well for this use case. However, most published visualizations use horizontal layouts, as publications have limited space, which often prevents such large vertical figures. In Net2Vis, we also employ such a horizontal layout. Modern neural network architectures not only contain linear execution steps. In turn, layer connectivity needs to be visualized. The most common encoding for such parallel execution steps is to simply draw lines between the connected layers. However, this induces size-related attention bias. To resolve this issue, we propose a modified glyph design with multiple handles to empathize these splits and joins of data flow. As modern neural network architectures can contain a large number of layers, they might still not always fit on one page. Since substructures in these networks are often repeated, aggregation is frequently used to reduce the complexity of an architecture figure. Net2Vis also allows for creating such groups, either automatically, based on recurring sequences, or manually, by selecting layers to be grouped. While this encoding conveys many features of a neural network architecture, we cannot encode all properties that might be of interest. For example, we do not encode the kernel size in our layer glyphs. The kernel size is often constant across many layers, which would lead to repetition. More importantly though, when creating groups from multiple layers, they might not all have the same kernel size, preventing such an encoding for these aggregations. Additionally, despite the fact that almost half of the surveyed visualizations encode layers as 3D glyphs, we chose a 2D layer encoding for Net2Vis. For relational tasks, like observing the transformation into and out of latent space, 3D encodings are less accurate. Three-dimensional visualizations also are less useful if the viewport cannot be changed, as is the case for publications. Additionally, almost none of the figures that use such a three-dimensional encoding conveyed additional information in the third dimension of the layer glyph. Let's now look at how this works in practice, and how you can create figures with Net2Vis. To get started, you simply paste your Keras code into the code area of the web application. Then, Net2Vis automatically updates its visualization. Here we loaded up a ResNet architecture. As you can see, this is a relatively large network. To simplify it, I hide some layers that are not important to understand the overall architecture. Next, I create groups, as these ResNets contain many repetitive blocks of computation. Alright, created two groups. Now, let's make it look a little nicer. I increase the height and width of the layers at display to make it look more like I want. Alright, a little bit wider. Cool, I think that's about what I wanted. Finally, to make it look exactly like I want, I changed some of the layer colors to reflect the color scheme that I want to have in my paper. We've done the same for our own paper teaser. We first imported the code into Net2Vis, then grouped and customized the visualization, and finally exported it to be used in our paper. We conducted a two-stage evaluation, where we first questioned 3 experts that authored publication containing such figures. Then, we conducted a quantitative user study with 10 participants. Experts mentioned that they felt like they were spending too much time manually crafting publication figures of CNN architectures. They complimented the advances of our visual encoding and explained how they were hoping for better tooling in this area. In our quantitative user study, participants were presented visualizations of different, well-known machine learning architectures. Each of these architectures was presented via 3 visualizations from different sources: Net2Vis, TensorBoard, and the original paper figure. Participants who saw all these visualizations in random order were asked to answer 8 questions about each architecture. After individually presenting these 18 stimuli, we asked 3 comparison questions where all 3 visualization methods were shown at once. Net2Vis scored significantly better than TensorBoard in both question score and time needed for answering, while there was no significant difference between Net2Vis and the handcrafted visualizations for either of those conditions. Net2Vis also scored best in the following comparison questions. After this evaluation, we also conducted a usability study with 16 participants. This indicated excellent usability for Net2Vis. For more details about our evaluation, please read our paper. To summarize, we propose a visual grammar for CNN architecture visualizations, which incorporates visual encoding, network layout, layer aggregations, and legend generation. We release a dataset of over 700 neural network architecture visualizations, which we have extracted from all papers published at ICCV and CVPR between 2013 and 2019. We provide an online platform which lets users automatically generate CNN architecture visualizations obeying to our visual grammar from Keras code. Now it's time for you to explore Net2Vis online and use it for your own publication figures.